You guys are early. All right, so let's go ahead and start. So we do have lecture today, of course, and there's a Google Meet session, but nothing else to say. But if you go back up a little bit, chances high that we might not be able to go over all the quizzes that I was expecting. So it could be just quiz 14 and 15, if we are lucky, 16. But the assignment that is probably more challenging this week is PA4. But if you get through PA3, fine. PA4 should be relatively easier. Okay? PA4 should be relatively easier. Now let's go down the topic list. We are not quite yet done with chapter 2. There's just a little bit remaining. CDN and 2 examples.
Okay, what's remaining are just 2 examples of how CDN requests are being redirected such that it reaches the physical location. So in the first example, it's more the Akamai model, which borrows from the services provided by DNS. So example goes like this. Bob requests a video from cinema.com, and this is the video ID. Okay, so browser here, browse around and decided, and Bob here hits this link. But the thing is that that video is actually stored here physically. The King CDN, a CDN company. And so it's stored on kingcdn.com's web servers, this location. But what happens here is, well, Bob's browser actually see this is the host to contact. So first thing first, ask the local DNS server for the IP address of this guy. Right? So resolve this guy. Bob's DNS server there will what? Check cache. If not a hit, go to the TLD server. TLD server will share what is netcinema.com's authoritative DNS server. And so Bob can direct the query to the authoritative DNS server for the IP addresses of netcinema.com. But what's really curious here is the authoritative DNS server of netcinema.com, instead of returning an IP address, it returns the redirected path. Okay. At this point, Bob's local DNS then resolve for this name instead. Okay. And so check the cache, check with the TLD server, and eventually reaching the King CDN's authoritative DNS server. That query goes, and finally now, King CDN authoritative DNS server will return the IP address of kingcdn.com. Okay, so IP address of this guy acquired, and step 5 sends that IP address back to Bob's web browser.
Okay, so let me pause here just a little bit. If you recall in the midterm exam, there was one question, right? I asked, we actually ping to www.amazon.com, but the returning host name and IP addresses are actually somewhere else, not quite Amazon.com. Here's why. Because Amazon is hosting the World Wide Web service in another company. Some of you find that it's fastly.com serving the hosting the web of Amazon.com. Some find that it's hosted by Akamai, one of the biggest CDN servers. Okay, and let's move on with the video.
From there, Bob's browser can fetch the video from the actual location of the video. Right? So this is redirecting the client to the copy through the DNS service. In example 2, the content provider here only needs to do the minimum, which is to provide the logging service. So Bob here as a subscriber just logging first. Okay, that's step 1. And quickly, Bob is redirected to the CDN. And in Netflix's case, Amazon's cloud is the CDN. So Bob here will be browsing what videos there are available, okay, and ratings and how long the videos are from the web servers Amazon has already set up. Now, once Bob has decided on watching a video, then step 3, the manifest file of that video is returned back to Bob. And Bob will begin to fetch the video from the physical machine Amazon has set up to store that particular video, and somewhat close to Bob. Last is just that the CDN server begin to dash over HTTP streaming the video. Now, if we compare the two models a little bit more, we see that in the first model, the content provider has slightly better control of where the redirections should go. But in the second case, the redirection is all done by Amazon. So there's not much Netflix needs to do, or not much Netflix can do. So it's more a trade-off between control and work. Okay? So more control, more work, less control, but less work. So, well, as a content provider, you'll have to decide for yourself.
So that was the last piece of chapter 2. And we move on to chapter 3, the transport layer. And that's begin. The overview video is a little bit long because I need to give all the necessary terminologies and the basic concepts. That's about 8-9 minutes.
You know what, Polly is just happy that we're starting chapter 3. The transport layer. We were at the application layer that's actually higher up. Transport layer, we're getting closer to the heart of the internet. So in the transport layer service, there are a number of important functionalities. Multiplexing, demultiplexing, reliable data transfer, flow control, and congestion control. Now each of these are important, but multiplexing, demultiplexing, flow control, these two are super simple. They'll be done in like one slide or a couple slides. Now, what's going to take us quite amount of time is this. Reliable data transfer. And then slightly less, congestion control. All right. And both of these functions are implemented in TCP. Reliable transport, congestion control. Now then you can imagine UDP being very simple, right? It's a connectionless transport layer service versus TCP being connection-oriented. So in UDP, you don't need to set up something ahead of time before we send data. But TCP, you need to have a setup process before we begin to send data packets. 3.1 is the overview section. So what I need to say here is this. The transport layer services is actually providing a logical communication channel between the two processes that are running on different end systems. All right. So there's a sender side of the process, a sender side of the transport layer protocol, and there's also the receiver side of the transport layer protocol. And the functions is often corresponding each other. Sender side will take messages from the application layer and break it into a number of these smaller segments. And these segments will be passed down further to the network layer. Receiver side is going to take segments from the network layer, reassemble them back to the original message, and that message gets passed up to the application layer. That's when, if this guy here sends an HTTP request, this guy over here receives the HTTP request. So the web server here can begin parsing the HTTP request and then find out what is the object being requested, right? So this is the very basic function of the transport layer protocols. Take messages from application, break it into segments, reassemble segments into message, and pass it back up to the application layer receiver. Now, that breaking of the segments, passing of the segments, and reassembling of the segments are implemented in two different flavors, TCP versus UDP. One is reliable, the other is not. Transport layer versus network layer services. So transport layer there works closely with the application layer. It works also closely with the network layer. But we have not yet talked about network layer functionalities much. So let me just, break it to you. What is the main role of these network layer protocols? So what they do is to provide communication between hosts. So meaning enabling sending of messages, sending of packets, or sending of segments through the internet and reaching the other host, the destination, from source host to destination host. Okay, so that is the purpose of network layer protocols. Transport layer, however, is just to establish a logical communication between processes. All right? So between two hosts, there are often multiple processes running. So transport layer handles a pair of processes at a time. So a pair of processes, and network layer handles a pair of hosts. The granularity, okay, of the channel, the entities of the channel are very different. Okay, so transport layer here rely on underlying network layer service. So if there's a process needing to send certain segments to another process, hey, how does the sending process know which way to pass it down further? Because internet is huge and in the middle. That is the network layer protocol's job. So logical connection between the sending transport layer and the receiving transport layer, that is kind of abstract. That's why I keep saying that it's a logical communication, because the network layer is going to handle and find a clear path between the two of them. All right. Now, let me try to use an analogy to explain so that it's more clear the distinction between a transport layer service to a network layer service. So the example is this. Anne here has 12 kids in the house, and Bill has also 12 kids in the house. Yeah, both big families. And for some reason, Anne's kids and Bill's kids are good friends to each other, right? So houses there, Anne's house and Bill's house, consider them as hosts. And each kid's generating letters sending to each other will be the processes. So 12 processes generating messages independently, okay, and trying to send them to Bill's houses and therefore reaching Bill's kids. So each letter generating by each kid is an application message. Anne and Bill will then be the transport layer service. So Anne here is the sending side of the transport layer service, taking all the envelopes and then drop it into the mailbox. So it's mixing all the envelopes into the mailbox. Bill, on the other hand, will take all the letters out of the mailbox and distribute each envelope to the destination processes, to each of the kids, right? So Bill there is demultiplexing the envelopes from the mailbox, and Anne there is multiplexing, okay, the envelopes into the mailbox. Now, the mailman, okay, taking all these envelopes from Anne's box and then go all the way to Bill's mailbox is the network layer protocol. All right, so mailman is the real person there needing to find a way and driving all the way to send all these messages. And there are two services again. TCP here does reliable transfer, but it actually does more. Packets are going to arrive in order. Packets, as they get sent, they will also be controlled. So sometimes you can send faster, but sometimes slower. And usually it's when there's congestion, then you send slower. If there's not congestion, TCP sender side will be sending more aggressively. There's also flow control, connection setup. Flow control is such that we do not overwhelm the receiver side buffer. Okay. Connection setup is, if you heard, TCP is a connection-oriented services as well. In order to provide these functionality, reliable transfer, in-order delivery, congestion control, and flow control, well, the sender and the receiver side of a TCP connection needs to, communicate a little bit more before setting up a connection. So that takes some time. So there's a connection setup process as well. UDP, on the other hand, is the complete opposite. It's not reliable. It does not guarantee ordered delivery. So UDP is essentially nothing versus TCP does a lot. So essentially at the transport layer, you have the two extreme of the services. Okay? So it's on top of the network layer, which is called the IP protocol, and it's best ever, meaning do nothing. All right, so no real extension of IP. And so UDP there is very simplistic. Take messages from application, break them into segments, pass it out. Receiver there, grab the segments from network layer, and then try to reassemble them back to the original message and pass it up to the application layer. Now, if there's any segment lost in the middle, that message gets passed up to the receiver side of the application layer protocol. It's not going to make too much sense, all right? Oh, and TCP UDP, one does reliable transfer congestion control, the other does nothing. None of them provide this delay guarantee, bandwidth guarantee, and none of them provide security guarantee. Okay, and you heard it earlier, the security is provided by this alternative service, but this alternative service is in fact implemented in the what? Application layer.
All right, so that was the overview. Let's go on and talk about the first important functionality, mixing and demixing.
3.6 multiplexing and demultiplexing. Well, if you still recall the end bill example, end kids sending to bill kids example. End is the multiplexer and bill there is the demultiplexer. So if we focus on this example below, so this guy in the middle is a big server machine. There are multiple processes running. You see here, P1 is sending a message out. P2 is also sending a message out. Yeah, the transport layer at the server is doing this, multiplexing. So this host here, from P1 and P2's point of view, generating this message, okay, is the sender. So sender. So it handles data from multiple sockets or data from multiple processes. Add the transport layer header. So add a little bit more information on top of these packets. Okay. And so therefore later they can be used for the demuxing purpose. So when messages go out and reaching P3 and P4, and P3, P4 in return generates something back as it arrives back to the server at the transport layer. Yeah, transport layer of the server is going to be working as a multiplexer at the receiving side. And what it does is to look into the header, okay, in these packets and then decide whether it should be this socket, the message being forwarded to, or this other socket, the message being forwarded to. So very simplistic, but very important functionality.
And that takes us to quiz 15. So you see two pictures here. A is what? The mailbox that's collecting all the mails that are supposed to go out. B is what? A mail woman there looking at the envelope, trying to sort the letters and drop them into each household. You know what? The postal system, how they deliver mails, works very much like how the internet delivers data. So Q1 is asking, consider the postal system. Which device is the multiplexer and which is the demultiplexer? Q2 asks a little bit further. Again, in the postal system, what is on the envelope that the mailwoman was looking at to allow her to demultiplex the mails? This is a very simple question. It's a short question. And as usual, we see Team 13 here very fast reacting to the quizzes. So let's see. Team 13 says A is the multiplexer and B is the demultiplexer. And then for Q2, receiver's address, including the postal code, right? So there's a receiver's address on the envelope, receiver's name, of course, okay, phone number, etc. All these can be used for the mailwoman to separate the letters coming to this address, coming to this building, and separate them so that they go to the right incoming mailbox to each household. Team 3, Mindy, says A is the multiplexer and B is the demultiplexer. For Q2, the address on the envelope, yeah, it works just like the header, right? So actually everything on the envelope indicating about the receiver as well as the sender is the header. And what's inside the envelope? The data. You know what? Have you tried to send a mail where you put a mail into another envelope, right, and ship it out? This is usually when you are forwarding mail, then you do it that way. Okay, so you can imagine that is exactly called encapsulation. You take a mail and put it into a bigger envelope, and then seal it, and then ship it out. Encapsulation. So you can imagine, right? The transport layer is taking a mail from the application layer and put it in another envelope. And what's a little bit weird, however, is that the transport layer sender is taking the mail from the application and break them into pieces, put them into another envelope and ship it out. Okay, so that is to give you a better idea what the transport layer is doing. All right. The functionality, very straightforward. Okay. Very good. I see answers flying in. Yes, this is not a trick question. This is not a trick quiz. This is just to let you know. Multiplexing, demultiplexing, multiplexer, demultiplexer. The term look strange, new to you, but we are familiar with the concept already. And let's move on to how the transport layer does demultiplexing, because multiplexing is straightforward. Demultiplexing is the part that is a little bit harder, but not all that hard. Let's take a look.
Now back to the lecture. If you think about it a bit more, multiplexing and demultiplexing, which one is more trivial and which one is less? Yeah, multiplexing, just collect the letters and shuffle it into the mailbox, right? No brainer. But mailman will have to, Bill will have to look at the envelope and see who the envelope is addressed to. So demultiplexing there is less trivial. Similarly, on the internet, the transport layer services receiver also needs additional information, just like names on the envelope, to do demultiplexing. So the information the receiver side of the transport layer service relies on are these. Okay, the source, destination IP addresses, and the source and destination port number. All right. Now, let me explain. The host that's receiving a packet, it's going to see this, the IP datagram at the network level. Okay, not quite yet at the transport layer. We are now at the network layer, the receiver's network layer. So what we're seeing there is a packet that we call the IP datagram. So let's call this the datagram. Okay. So now a datagram is composed of the header part and the payload, the data part. Okay, so a header here and data here. Inside the header, there are these fields, the source and the destination IP addresses. Okay, so these information are kept there. So it's a network layer information. And each datagram also carries a transport layer segment, which is this, the data part of the IP datagram. So this here is exactly what's depicted on the side here. It's a segment. Similar to datagram, a segment is also composed of two parts, the headers and the data part. Okay. So the segment's header contains source and the destination port number as well. Right? So source destination IP together with source destination port number, they are the information to allow the transport layer services the receiver side to do demultiplexing. Okay, I hope this is clear.
All right, and there are two kinds of demultiplexing. Sorry, a wrong click. Let me go back to, yeah, two kinds of demultiplexers. Two kinds of demultiplexing. First one, easier.
And the first form of demultiplexing is called connectionless demultiplexing. And this is also the kind of demultiplexing being carried out by a UDP connection. All right. So in this type of demultiplexing, we rely only on the destination IP address and destination port number to decide which socket to pass a packet towards. So it's only a two-element tuple. Right? So when a host receives an UDP segment, it checks the destination port number in the segment and then direct the segment to the socket carrying that port number. And that's pretty much it. Okay. Now, of course, the IP address is important because the host at the network layer would be able to decide, whether this particular host is the destination of this packet, therefore keeping the packet and pass it up to the transport layer. And the transport layer could handle this. Yeah, receiving a UDP segment, check the port number, and so on and so forth. All right. So datagrams with different source IP address and different source port numbers, as long as they come to the same IP address, same destination port number, they will be going through the same socket. Okay. So demultiplexing for UDP is slightly simpler. All we care about is the destination address and port number. So here's an example of connectionless Demux. So port 9157 is where P3 is sitting on. So that's one of the clients. Port 5775 is process P4 that is sitting on. So that's another client. Server in the middle, open up a port number 642A, and P1 there is the server processing. It's waiting for requests to come in. So we see here a service request message being generated from P3 and intended for P1. You will see source port number being 9157 and the destination port number being the server's port number 642A. And the return messages, so replies from the server would then be carrying the source port number being the server's port number and destination port number being the sender's port number, the original request sender's port number, 9157, the client's port number. So you see also a little bit that how P1 can generate the reply. The port numbers are essentially the reverse, okay, of the requests. Now, if there's another request coming from P4, what is going to be the source port number? 5775. And destination? The server's port number. And it's probably not hard. The returning messages back to P4, source being 642A, essentially the reverse of these two port numbers. The slightly more complicated one is the connection-oriented Demux. That is also the TCP's demultiplexer. So whether a packet or a segment should go to a particular socket depends on all four information. All right, so receiver uses all four values to direct the segment to the socket. Now, a server process running there on the host could be maintaining multiple sockets, okay, for each pair of communication per client. So, for example, a web server, the web processes there could have multiple sockets open for each of the connecting client. And if this is older form of HTTP the web server is running, it could be one socket per object request. Now let me use an example to illustrate and explain. So we have a scenario where we have three segments being sent from clients over here, A and C, to the server in the middle, B. So all three segments destined to B, and they're supposed to be demuxed into different sockets. Now, P4 sockets will be using a 4-tuple to decide. And what will be the 4-tuple? Well, source IP address, A. Destination IP address, B. And what? Source port number and the destination port number. So these 4 values is going to be associated with this socket. So when there's a segment arriving at the transport layer, matching the 4-tuple, therefore going to the socket. Similarly, for each of the socket here and there, the 4 tuples will be stored, and the transport layer looking at the packet header, when there's a match, pass it up to socket to the processes. So that's the idea behind connection-oriented demux. And the reason it's called the connection-oriented demux is because it's not only looking at the destination, it cares also who the sources is. So it's almost like there's a one connection between the source and destination already, okay, the socket. Now, this connection-oriented demux socket is a little bit weird. And this actually happens quite often these days when we're doing this threaded server. Okay, so in your PA4, you are implementing a server, all right. What happened there is that you are starting a listening socket, isn't it? Listening socket is a little bit special because no matter where the client is, whatever the source IP is, request coming in is going to be passed to that server socket, that listening socket, all right, even though, the 4-tuple does not quite match, especially the source IP address and the port number. Okay. This type of connection-oriented demux, it is TCP, all right, but it only looks at the destination port number and the destination IP address. Therefore, the message is coming out this way. Source being A, source port number 9157. This one here, source being C, port number again different. But then they will all be accepted by the listening socket here.
So that was multiplexing, demultiplexing. It's the most fundamental functionality in the transport layer, although it's quite straightforward. And we now talked about individual protocols, and first starting from UDP, the easier one.
UDP stands for User Datagram Protocol. As we've discussed many times, UDP does pretty much nothing on top of the network layer basic service. So we could have segment lost, we could have segments arriving out of order. So no reliability, unreliable. Second characteristic of UDP is this: it's connectionless. Therefore, there's no handshaking, there's no connection setup phase, there's no connection setup delay. As soon as we have data to send, we just generate these UDP segments and push it out. Very low delay. While we have also very low reliability. Right. But hey, some applications would actually like low delay, and it probably doesn't care too much about reliability. Then these applications would be perfectly fine using UDP as the transport layer service. So some of the video streaming services, some of the gaming services that we talked about uses UDP. Skype's voice sometimes also use UDP. DNS, getting the host to IP mapping, we need it as soon as possible. Therefore, UDP here. Now, if one of these DNS query or reply is lost, DNS server, the local DNS server is going to send another request real fast, so don't worry. And SNMP, okay, we have not yet talked about this protocol. It's called the Simple Network Management Protocol. Now, this protocol is talked about in the textbook, but it's in one of the later chapters. Most of the content there is to talk about building a database, defining the format, such that when we measure, for example, round-trip delay from one host to another host, we get to store these round-trip delay data. We get to store packet loss rate data. We get to store available bandwidth measurement data. Right? So SNMP there define these data structure for informations that measures the performance of the internet. SNMP also gets set up across all the machines around the world. If they are enabled, these machines will send these SNMP messages back to the SNMP database. And those messages are sent using UDP because after all, these informations are nice to have, but they are not really necessary there to ensure the internet continues to operate. It tries to help such that the internet can perform a little bit better. But without these messages, the internet usually works just fine. Right? So those messages are also in UDP. Last point here. Yeah, UDP does not do reliable transfer, but some applications might need reliable transfer services, but not 100% reliability is required. Then those might add the reliability at the level the application desires, okay, and does application-specific error recovery. So this is one of the reasons people use UDP. Not only because some applications doesn't care about having segment loss, some applications wishes the messages being really fast, and some applications want some level of reliability but not perfect reliability. There's some other use of UDP. Right? So some other advantages of UDP. There's no connection establishment as we know, low delay. It's very simple, there's no handshake. It's easier to implement. There's also a small header. So this is a UDP segment. Once again, there's a header part. There's also a data part. The header part, very small. Just two 30 bits, 64 bits altogether, and that is 8 bytes. Very small. There's no congestion control, so you can actually blast into the internet as fast as possible. All right? So these are a few other advantages of people using UDP. Okay. So there are 4 fields in the header. The source and the destination port number, which we've already talked about. The 2 other fields we have not yet talked about is lengths. This is the size of the UDP segment entirely, including header and data. And the unit to count the length is byte. Last is the checksum. What's interesting about UDP is that, hey, if you send it out over UDP, there's no guaranteeing of reliable transfer. But you do get this. You get to check whether there's any bit errors in the data part of the UDP packet. And this is the way it works. It's called the Edp Checksum. This is how it works. At the center side, we take the segment out. Okay, so take the entire segment, including the header, and lay the bits 1 row at a time, and each row 16 bits. So it looks a little bit more like this. Yeah. A row of 16 bits, another row of 16 bits. Okay, so you lay them out and then do what? Summing, okay, of these 16-bit rows. So add them up, and to be precise, it's called the ones complement sum, to be exact. Okay. And as a result, you get also a 16-bit output. That is called the Edp Checksum. Right? So let's come back here in the example to explain how exactly it's done. So sum, binary add, 0 plus 1 writes 1 here, 1 plus 0 writes 1 here, 1 plus 1 writes 0 here and carry 1 over here. That's why, even though these two are zeros, we still get 1 down here. Okay, just do the binary addition all the way to the end. Now, there could be extra bits being introduced. No worry, what we do in the once complement sum is to wrap this around and then add back to the number here. So that 1 being added here writes 0, carry 1 over, writes 0, carry 1 over, writes 1 here, and that's the end. All right. Now the last thing is just to do what? To the complement. All right. So complement is straightforward, flipping 0 to 1 and flipping 1 to 0. And so in the end, we ended up having the checksum, which is also 16 bits. And this is what's being placed in this part of the UDP segment. All right. So when that UDP segment arrives at the receiver side, receiver does the exact computation, take the segment out, and compute the checksum. That checksum after computation is compared to the checksum field in the packet header. Right? If there's no bit error at all, right, the two checksums should match, isn't it? So if this equals this, if yes, then there should not be error. But now be careful, there could be specific bit error patterns that the checksum might not detect. Okay, so maybe error, but chances is very low. All right. But otherwise, if the checksum do not match, so there's clearly some error. Okay, so application layer there, finding a UDP segment having mismatching checksum can at least discard the packet, discard the segment, knowing that there's already something wrong. Right?
All right. We do have a couple questions, and I will address these questions during the break. And let's move on to talk about reliable transfer that's implemented in TCP. But to talk about exact mechanisms in TCP, let's introduce the principle, because it's not trivial at all. In fact, this is the part that we'll be spending maybe more than a week time on. It's called RDT, Reliable Data Transfer. Okay, and we'll start from learning the notations and the system we'll be using to explain RDT.
All right, 3.4, Principles of Reliable Data Transfer. Now, you might see Polly is a little bit more alert talking about this section, because this is going to be the most challenging section in Chapter 3. And arguably, one of the most challenging sections for the entire textbook. All right, so let's talk about reliable data transfer. It's not only challenging, it's also extremely important. All right. So it's not only important at the transport layer, some of the link layer services might also implement some level of reliable data transfer. At the application layer, someone might be using UDP as the underlying transport layer service and implement its own reliable data transfer. So maybe it'll be more efficient than TCP instead of using the native TCP provided in the protocol stack. All right. So it's one of the top problems when one needs to design a communication network. Now this is the setting. We have processes sitting at the application layer. Okay. There's application layer protocol, but there's also transport layer services. These processes depend on to transfer application level messages. So sending processes here, sending out data. Data will go through a channel. Now this is reliable data transfer service, so the channel is reliable. And hopefully at the other end, the receiving process grabs the data and then interpret the data, and things will just work out. Okay. But the thing is, the internet is not exactly reliable, isn't it? So yeah, we do have unreliable channel when packet goes through the internet infrastructure. Now, but application, sending process, receiving process are demanding reliable transfer. So transport layer service here, the sending side and the receiving side each will need to implement some extra mechanism to ensure somehow lost segment is recovered. Somehow the flipped bits are corrected. Right? So that is RDT. Okay, and we're going to go through a few generations of these RDTs and show you how the sending side is implemented, how the receiving sides can be implemented such that we provide such a illusion to the application level services. Oh, and by the way, it really depends on how unreliable the channel is underlying. Then the complexity of the reliable data transfer can vary. Very unreliable, very complicated. Not that unreliable, then slightly simpler. Now, we'll be using these notations, RDT send, UDT send, and all these throughout the discussion, introducing you generations of these reliable data transfer protocols. So let me blow it up and explain a little bit further. All right, so sending processes here, generating messages. Those messages get passed down to the transport layer, and those messages are now called data. All right, and RDT send is the function called the sending process calls to pass the data down. Okay, so let me bring it up. RDT send here is to be called from above, from the sending process. Okay, and it is to pass the data down such that it will arrive at the receiver end. Good. Well, and these messages is going to be processed here, and a number of these segments will be generated, or packets will be generated. So when we're talking about generally reliable data protocol design, let's just call these packets. Okay, so messages now data, segments is now packet. And the action of pushing the packets down to the unreliable channel is UDT send. Okay, UDT send. So UDT send here is called by the RDT, the protocol sending side, to transfer packets over the unreliable channel. All right. And then, yeah, data is going to travel through the channel and come to the network layer. So that network layer component would call this, okay, RDT receive, to pass the packet further up. So packets gets passed down by calling UDT send. Packets gets passed up, okay, by calling RDT receive. Okay, and this is called from below, from the network layer, when packet arrives. And those packets will be processed here, okay, and then the receiver side of the transport layer protocol is going to call yet another one, receiver data function. So this is called by RDT, the receiver side, to deliver data to the receiving process above. So data here is going to be passed above. So 4 function calls to refer to actions. First, coming from the sending process to the sending RDT. Second, from the sending RDT to the unreliable channel. Third, from the network layer to the receiving RDT. And the fourth, from the receiving RDT back up to the receiving process. Now, we'll try to describe generations of these reliable data transfer protocols. As Polly mentioned slightly earlier, yeah, these various generations, one is simpler, second slightly more complicated, third even more complicated. So they go from simpler RDTs to more complicated RDT. That's because we assume the underlying channel being more reliable to less reliable, to very, very general, like the internet. All right. So that is just to prepare you for the RDTs that we need to introduce coming ahead. Now, another thing that I need to introduce is how I'm going to describe these RDT mechanisms. We're going to use, this thing called the finite state machines. Okay. Finite state machines, FSM. Okay, so here's one state, here's another state, two states. So finite number of states. All right, so this is a machine to go from one state to another station, from one state to another state. You might have a transition saying that under this condition, then we go from state 1 to state 2. And in the meantime, we transit from one state to another, we take this action. Right? So the arc here defines when will a machine jump from one state to another, and what is the action to be taken corresponding to this event occurring. Right? So at each state, there could be number of events, okay, that could trigger the state changes, and that could also trigger additional actions to be taken. Okay? So provided a machine, a mechanism, usually engineers can describe the mechanism using a finite state machine like this. All right. So FSM is also, if you recall, formal method, finite automata. When you're taking these courses, finite state machine is a notation that you should be familiar with, because it's a way to describe a computational machine. Okay? And it's to describe it in a more formal way. Provided the machine, then the implementation will be straightforward. It's a little bit like when you take an algorithm course. After you learn how to write a pseudocode correctly, provided the pseudocode, your programmer that you hire will be able to program. Okay? That is the only thing that's required to communicate to the programmers. Oh, there's one more thing I neglected to mention. Yes, we only consider a unidirectional data transfer. So what I meant there is that one machine to another machine, data is going one way, and there's no data coming back. Okay, so data go, receiver, okay, and receiver might send feedback back. Those are called the control info. Okay, control info can go both ways, but data only go from the sender to the receiver. All right.
Okay, a little bit intensive. We'll try next, looking at some of these finite state machines next. But before that, let's take a break. It's now 11:12. Allow me to borrow 2 minutes today so that we could try to go through the RDTs all the way to version 2.1. So we could have the quiz 16. So let's resume the lectures at 11:20. So feel free to go out and take breaks. But in the meantime, let me try to address Ida and Weiyo's questions. So Ida was asking, is there any protocol guaranteeing delay? Oh, okay. Yuting was asking another question. So feel free to type up the questions as others are taking breaks. So Ida, unfortunately, in internet, at the transport layer, there's no protocol guaranteeing delay. If we do want to guarantee delay, yeah, we need to do reservation-based connection. That is increasingly hard to do on the internet as it grows big and complex. So unfortunately, no guarantees for delay. But on the internet, what people try to do is to try to reduce delay as much as we can. So instead of guaranteeing, try to improve the end-to-end delay. Second question from Weiyo. Oh, why are there sum and checksum? Okay, so now you heard about internet checksum. It's what? One's sum, the binary sum, and then take a complement. It's actually a sum. Yeah, it is a sum. The reason that we call this checksum, the computation, the calculation is a sum. It's a special form of summing numbers up. But we call it checksum because we actually check this number to verify whether the data is correct. Okay, so the differentiation is just that this particular sum we're using is for checking. Okay, it's not to really quantify certain substances. Okay, so we're not counting number of bits we're sending. We're checking whether the bits are correct. Okay, so we have different terms referring to different things. Yuting, why is that in the RDT graph there is a double way error beside UDT send or RDT receive? Okay. Maybe I can go back to the slide and we can discuss a little bit better with the picture, okay, with the graph. So let me bring up the graph, Yuting. Just 1 second, we're almost there. Yeah, I think it's this graph here. Yeah, I think you're seeing this, right, Yuting? So I think you're referring to the UDT send, whether the errors are two direction. I think you're right, okay? Because I added in the end that the data is going one direction. So that error should just go down, isn't it? So the UDT send here, this error should just go down. You know what? That's true, because packet is definitely going down. But you see, because we have not yet talked about it, Yuting, when the packet goes down to this end, the receiver side of RDT might actually send something back this direction. Okay, so we have not yet talked about, well, there could also be packets coming back up. But those packets are not exactly the segment packet. Those are more like feedback packet to the sender. Okay, so Yuting, very good observation, right? I try to explain, right? Data go down this way to the receiving end, and why is there a two-way error here, and in fact here and here? Because there are some packets coming back. Okay, but you know what? This is definitely one way, and this is one way as well. The transport layer, RDT sender side, receiver side, either one does not send anything back up except data. I hope that it's a little bit more clear because we have not yet talked about it, but very good observation. It's very counterintuitive. Jiawen here asks, what is the difference between reliable and unreliable channel? Is it related to error? Yes, it is, Jiawen. When we're sending data, if the underlying channel could have errors, for example, if we send data through wireless channel, chances high that the signal to noise ratio low, we cannot, identify correctly what exactly the bit is. Is it 0 or 1? Yeah. So unreliable channel means there could be bit errors, and sometimes the bits just don't get through. So unreliable channel meaning there could be bit errors and potentially bit loss entirely. A reliable, then it's the opposite. Okay, no bit error, no loss. Oh, Weiyo has like a Weiyo has a follow-up question, I guess. Why do we need to complement it at the end? Okay, that's a very good question, Weiyo. It has something to do with implementing it. As human beings, doing the ones complement sum, it's actually a number of two additions and a complement. Okay, 3 operations. But if you think about, recall logic design, one can probably put some add, complement, or gates together, and the structure can be very small, and so that doing the ones complement sum is very easy. Okay, so ones complement sum is often used And there's usually a hardware chip that's accelerating the computation. So for human beings, it's definitely slower to compute than just summing the two binary numbers up. But once complement sum can be very easy to do in terms of implementing a circuit for it. All right, so Boris is asking, I wonder if there's RDT 3.1 or further, because I only see in the end of this chapter. No, there's no 3.1. There's just 3. Yeah. Okay, good. Oh, good. You're welcome, Yu Ting. Okay, good. And you know what? Perfect time to come back. So finally, let's move on to the first version of RDT, which is a little bit trivial. Sorry about that.
And now, RDT 1.0, the generation number 1. Right. So in this generation, yeah, the assumption is very strong. We're simply assuming that the underlying channel is reliable. As a result, sending side of RDT, receiving side of RDT, there's nothing really needs to be done. So the machine is very simple. So this RDT 1.0 is just so that you are more familiar with the finite state machine notation, right? So underlying channel is perfect. No bit error, no lost packets. Okay, so the sender side of the finite state machine, FSM, will look just like this. Okay, so there is always at least one state that is also the starting state. There's no ending state for these machines because they'll be looping forever. Okay, so starting state is wait for call from above. Okay, so application calling data to be sent to the transport layer. So yeah, calling from application from the sending process is RDT send, isn't it? So when you run into this event, the sender there, yeah, would generate packet out of data. So data is the thing coming from the application. And packet is generated to be pushed out. And to push down, we call UDT send. Right? So this is the FSM at the sender side. Similarly, at the receiver side, call from below. Right, so when that is happening, yeah, RDT receive being called, receiver side of the RDT 1.0 will just extract data out of the packet and deliver the data up to the application layer. All right, so again, events triggering changing of state, and the arc direction indicates which state it changes to. And so a loop coming back is saying that, hey, we stay at the same state. Right. In the meantime, we take these actions. So event triggering the transition. In the meantime, we make the transition take these actions. So you see, sender side keep being triggered from the application, calling this and triggering actions to occur, triggering the state being changed. So that is the general idea of FSM and using it to denote a functioning machine. All right. Sender sends data into the underlying channel. Yeah, here. Receiver sends data from underlying channel. Yeah, here. All right.
So that was 1.0, very trivial, as I said. Now, let's make it a little bit less trivial, assuming the channel is unreliable.
And then RDT 2.0. So this is when the channel is no longer perfect, but it's not so bad either. We do have some problem, but just this problem, having bit errors, meaning the packets, okay, if you look inside, some of the bits might be flipped. Therefore, it failed passing the checksum at the receiver. So the computed checksum and the packet header checksum somehow didn't match. Receiver then detect bit error. The question is, how do we recover from this error? Well, if you're thinking how to do this in the computer in the transport layer, I'm sure that it's very hard. But if you think this, how do humans recover from errors during conversation? Say, if Polly was trying to describe finite state machine and it sounded really fuzzy to you, what would you do? There you go, right? You type up in the live chat and ask, hey, what do you mean transition? What do you mean changing from state to another state? What do you mean certain event occur and triggering the changing of the state? It's not clear. And Polly then will try to explain again, right? Retransmit the packet again. So, sure, if you abstract this exchange of feedback and data and retransmission, you see the general idea seems to be receiver upon detecting error, sending feedback to the sender. Sender retransmit the packet again, and hopefully the second time it's clear, no longer fuzzy. That is the general idea of RDT 2.0. So to describe RDT 2.0 a bit more formally, those feedback you're providing to me, in the computer system, they'll be either in this form or this form. So acknowledgement there is a positive feedback. Negative acknowledgements, therefore, the negative feedback. Acknowledgements there or acts there are to explicitly telling the sender everything is all right. And next here is to tell the sender, something's wrong, and therefore the sender can retransmit the packet. Okay, so retransmit of the packet is triggered by the receiving of next. This is exactly what's defined in RDT 2.0. So let me stress, there's first, detecting error, second, sending back of the feedback from the receiver, and then retransmission of packet coming from the sender in case negative acknowledgement is received. Now, what's a little bit harder is to go over RDT 2.0's finite state machine. All right. Now, try to be a bit patient here. Let's focus on the sender side of the FSM first. This time, we do have two states. One is wait for call from above. Oh, okay, this one is familiar, right? So this is the initial state. The sender is waiting for the application process to send data down to the transport layer. Okay, so wait for call from above. And there's gonna be a transition triggered by this event, RDT send, the application calling and having data to send. The sender here, transport layer, will then create packets from data. And this time, in order to detect error, we need to add the checksum. Right? So, hey, this is very abstract, but you get the idea. When you're generating the packet, we do need the data from the application layer, but we also need to compute the checksum. All right, so when we generate the segment, make sure that the checksum is somewhere in the header. Very good. So send packet is finally generated. So this is the segment. And sending side of the transport layer service calls UDT send to send the segment out through the underlying channel, right? And that also take the sender from the wait for call from above state to the what? Wait for ACK or next state. Oh yeah, so after we send the data out, then we'll be waiting for feedback from the receiver. Good, makes sense. All right. Now, hey, here, what's coming back as feedback could be positive and negative. So therefore, you see two transitions possible, one over here and the other over here. So this is the negative feedback case, and this is the positive feedback case. Now, the easier one is if the feedback coming back is positive, right? So this is when the sender receives a message back from the network layer, so it needs to be triggered by call from below, RDT receive, the receive packet. And you check whether the receive packet is positive. So if both conditions true, then hey, do nothing. So this is empty set do nothing, and then return to wait for call from above state, meaning, hey, positive feedback, so move on with the lecture, for example, so to speak. Right? So, hey, Polly can actually teach more next. But if the feedback is negative, so if some of you say, hey, wait, no, not clear. Can you do this again? Can you talk about it again? Well, in that case, okay, RDT receive, called, and the feedback is negative, what? Yeah, Polly resend the packet. So UDT send, the packet that's generated being sent already once will be, sent once again. Okay, so it's a retransmission. Now, what's a bit interesting is this. When we're at the wait for act next state, when we receive a negative feedback, we actually come back here again to wait for feedback. So hopefully the next one is going to be acknowledgement, and therefore we can leave the waiting for feedback state. Right? So that was sender side of RDT 2.0, the finite state machine. Now let's move to the receiver side. All right. Whew. There's only one state, cool. But there are two different transitions, one above, the other below. So they are both triggered by RDT receive. So receiver there would be, call from below, from the network layer, saying that network layer, I'm here and I got the segment for you. I got a datagram for you. All right. And then you grab the datagram, remove the IP header, and you see the segment. You try to do the checksum computation, isn't it? Right? And there are two different conditions. One is if the packet does have bit error, meaning the packet is corrupted, then you need to do what? Send the negative feedback. So UDT send. So UDT send is what? To send the data down to the network layer. And so receiver there sending the data down to the network layer. Network layer is going to send it back to the sender. So UDT send NAC is the action being triggered. And receiver comes back to wait for call from below. So it could be a correct data packet. It could be a incorrect data packet, depending on which is the case. So incorrect calls this arc. Correct calls this arc. If it's not corrupted, extract the packet. Okay, extract the data out of the packet, deliver the data up to the receiving process, okay, and then send back positive acknowledgement. All right. So sending feedback. But if everything is correct, the receiving part of the transport layer, receiving part of RDT 2.0 is yet to extract data and pass it further up to the application layer.
All right, hope you are coping fine with the finite state machines. Let's take a look at an example using RDT 2.0, because you kind of have two machines, one at the sending side, one at the receiving side, working simultaneously.
Okay, now let's walk through a couple examples to show you how the sending side and the receiving side of RDT interacts. Okay, so this is RDT 2.0. And this is an example showing that, hey, there's no bit error in the packets. So, originally, okay, the sender starts from the initial state, wait for call from above. Receiver here also, starting here, wait for call from below. All right, so now we get a call from above. Okay, RDT send being called from the application layer, the sending process. Now, sender side would actually take the data, add the checksum, and create a packet, send packet, and then call the UDT send to send it out. Right, so go through that, and that packet is going to arrive at the receiver end. Receiver side of RDT 2.0 will be called. Okay, but there's no error. Okay, so this is the no error case, so it's going to pass this condition, receiving a packet from below and it's not corrupted, therefore triggering these actions being taken. data extracted out of the receive packet, delivered to the receiving process, and send back in positive acknowledgement. So let me remove the notes. Yeah, so we'll be triggering this transition and all these actions, and that message is going to come back here. Okay, so you see it flashes, but essentially we were waiting here, right? And that packet, egg packet, is true. Therefore, both together is true. And we do nothing and simply return to wait for a call from above. So this is the case between the interactions of the sender, RDT 2.0, and the receiver, RDT 2.0. Okay, let's do it again. Oops. Okay. At the beginning, here, starting state, here, sender gets call from above, triggering these actions, taking a transition, and message is going to reach receiver here. Okay, and it matches this condition. Therefore, these are going to be triggered, and we stay in the wait for call from below state. And this is going to generate a message being sent back this way. Yeah, and because it's an ACK, therefore we trigger this transition, and the sender goes back to wait for call from above state. All right, so this is the no error example. The next example is more interesting, where there is error. So similarly, sender starting from wait for call from above state, receiver starts from the wait for call from below state. And yeah, there's a call coming in, okay, generating the packet, send the packet out through the network layer. Straightforward. So this event match and these actions taken, and we take the transition and move to the wait for ACK or NACK state. And that's going to generate a packet to the receiver. And this time, yeah, this event is triggered. Network layer says, I have a packet for you. And which of the condition matches? Well, we have error here this time, so it's corrupt. Therefore, we trigger this transition to occur. Condition match and this action, and then stay in the same state. So we'll be calling UDT send, and we are sending a negative feedback, the NAC. That's going to fly back. So sender here waiting in the ACK, waiting for ACK or NAC state, then gets a call from below. And it's checking and finds that it's a NAC, not the ACK. Therefore, this transition matches and being triggered. This action is being taken. So UDT send packet is what? Retransmission of the send packet generated earlier. Okay, and sender here stay in the wait for ACK or NAC state. So this is taken and packets being sent again. But the second time, yeah, we're lucky. Second time it's not corrupted, therefore we trigger this transition and another packet being sent back. And this transition now, because of the condition being matching, yeah, we do nothing and we return. The sender returns to wait for call from above state. All right, should we do it again? Oh, probably not, right? You get the idea. Okay, so the interaction between the sending and the receiving machines of RDT 2.0, how they interact. Okay, so there are actions being triggered, and in the meantime, packets being generated, and they would go to the other end, and feedback being generated, coming back to the other end.
So that was 2.0. Hope it's still culpable. Okay, we do have two questions. I'll hold on to the questions and try to address towards the very end, because some of the questions you guys are asking, if you just wait up, I'm just gonna talk about them. All right. Okay, very good. Keep asking, definitely. Just show that you have these questions, and other students seeing the questions will know that, hey, they are normal. Okay, you're supposed to have these questions. But I can see also that some of these questions are to be addressed in RDT 2.1 or RDT 3. Let's move on and listen to RDT 2.1.
But RDT 2.0 has a fatal flaw. Yeah. If data can be corrupted, therefore a receiver needs to send ACK and NACK to provide feedback to the sender. The ACK and NACK coming from the receiver to the sender, those packets can also be corrupted. So what if that feedback packet is corrupted? Then sender will not know whether it's really an ACK or a NACK. So, wow. So should the sender retransmit, or should the sender say, okay, I'm just gonna wait for another call from above? Dilemma. So what do we do with this? If you think a little bit further or recall back, didn't we have the same situation, right? So when data is corrupted, we ask the other end to send feedback. So perhaps we could ask the sender of the data to send feedback so that the receiver will know whether the ACK or NACK is corrupted, therefore retransmit the ACK or retransmit the NACK. Yeah. So how did we deal with the corrupted data? We do the checksum, right? At the receiver. Well, actually, we do the checksum at the sender, adding that into the packet, and receiver check it again. Now, if it's not a match, we send NACK. If it's a match, we send ACK. So this is receiver side action. And therefore, at the sender side, we could retransmit data. So perhaps we'll do this, right? So ACK, NACK corrupted. There's potential. So why don't we do checksum, okay, on the ACK, NACK? So receiver there adds checksum for the ACK, NACK. Sender there checks if the checksum matches. And sender, upon seeing a mismatch, sends a NACK for the ACK or NACK. If it's a match, sends an ACK for the ACK or NACK. Therefore, data receiver there can retransmit the ACK and NACK. Oh, makes sense. But if you think a little bit further, how do we ensure that the ACK NACK for the ACK NACK is going to arrive back at the receiver, right? What if these guys are corrupted and therefore the receiver will not be able to tell whether the former ACK NACK being sent is corrupted or not? Exactly. What happens if the ACK NACK of the ACK NACK gets corrupted? Okay, so you have circular dependency there, and the problem never gets solved. So alternative thinking coming next. The new thinking to address the circular dependency we saw earlier is this. The sender, okay, will just not figure it out, okay, whether it's ACK or NACK being corrupted, okay? So sender will just pretend to be dumb and not trying to ask for a clear answer. Sender here instead retransmit the data that's already sent to the receiver. Would that work? If the corrupted ACK NACK is a NACK, then hey, this addressed the issue, isn't it? If the corrupted feedback is an ACK, then this actually creates duplicates. So the receiver side, in case it being an ACK feedback being corrupted, might have duplicate data. So this is actually not good because at the receiver side, it's going to receive segments one after another. And it's just going to reassemble everything and then pass it up to the receiving process. If that's the case, you might see typos, duplicated sentences, duplicated phrases here, there in the document, or sometimes duplicated pictures or partial pictures. Okay. So in RDT 2.1, to really seriously addressing the issue, we need to add a sequence number to the packet sent so that the receiver side can check the sequence number and see if the packet that has already been received earlier matches the sequence number that I'm receiving now, the receiver is receiving now. If they match, then that is very likely a duplicate from the sender, okay? And the corrupted feedback is an ACK. Okay. So, entirely in RDT 2.0, sender will just retransmit the current packet in case the feedback is corrupted. But in the packet, it's going to carry a sequence number that will allow the receiver to tell whether this is a duplicate or not. In case the receiver detects it's a duplicate, it would scar the duplicated packet. And this is RDT 2.1. And there's one more thing we need to talk about. That tells a little bit about the sequence number requirement here. Think a little bit more. RDT 2.0, RDT 2.1. The sender behaves this way. After sending one data packet, it's going to stop and wait for feedback until everything is cleared. Then it will go back to send data again. So sender sends one packet and it's going to wait for feedback until everything is cleared and move on. So you see, if the receiver during the phase in stop and wait state receiving two packets carrying the same sequence number, then that must be a duplicate due to a corrupted ACK, isn't it? Yeah, so sequence number in such form of reliable data transfer is very simple. It needs only one bit, two numbers, 0 and 1, to tell whether it's a duplicate apart from a new packet. Now, judging from the description, it sounded somewhat easy, not that complicated. But if we look at the finite state machine, it looks somewhat complicated. And you know what? This is only the sender side of the FSM. We have not yet looked at the receiver side, all right? So this is the sender side of RDT 2.1, which is the version of reliable data transfer that handles corrupted ACK coming back from the receiver. Now, the easiest way to look at the finite state machine here is by drawing a line separating the two mirror parts. So if you look at the upper right part of it, this looks like the wait for call from above state in RDT 2.0 sender, isn't it? And wait for ACK and NACK, this looks like the waiting for feedback state in RDT 2.0 sender. If you go down further, this other half, it's actually very similar. Wait for call from above, and then wait for ACK/NACK. Okay, the only difference is this. Wait for call for packet 0 from above versus wait for call for packet 1 from above. We just talked about the sequence number required to separate two packets one after another. From a duplicate, a retransmission of an existing packet, isn't it? So having 0 and 1 is a way to tell duplicate packet apart from a fresh packet. So we do need to have the separation here in RDT 2.1 sender. And as a result, when we get a call from above, so application calls RDT send data, will then trigger these actions to occur. So we'll be making packets, taking data, and we do the checksum, right? So this is in order for the receiver to check and see if the receiver sends ACK or NACK. The new thing we add here is, to add sequence number to the packet we're creating. So the send packet here now contains not just data, not just checksum, but also a sequence number. And as usual, we send it out through the network layer. So we call at the transport layer called UDT send. Now, the second thing that is a bit unusual is also this. Hey, the feedback state, wait for feedback state, you see, wow, the condition looks all complicated. Yeah, particularly if you see, we're now checking first whether the feedback we receive is corrupted or not, whether it's actually intact or not. So this is the case when it's corrupted. This is the case when it's not corrupted. So if we receive a packet from the network layer, receive a feedback packet from the network layer, and we check that it's not corrupted, everything is fine. And that packet is a positive feedback. That means what? Transmission of packet 0, perfect. So we do nothing and then we move on to wait for call from above again. All right, so this transition here is straightforward. Now, what is a little bit unstraightforward is this transition. So this is the transition that we come back to wait for feedback again. Okay, so these are the complicated cases. You see here, if the ACK or NAC coming back is corrupted, what do we do in RDT 2.1? We'll just retransmit the packet that's sent once earlier, isn't it? So if it's corrupted, simply send it again. So the sent packet here is not actually being reassigned. So it will be the packet we have sent earlier. So it will be carrying sequence number 0. There's another condition. If the packet is not corrupted, but it is a negative acknowledgement, then it's just like in RDT 2.0, we retransmit. All right, so this transition here gets, doubled. It's checking two conditions. If it's not corrupted, a negative acknowledgement, retransmit. If it's corrupted, also retransmit. So we have two conditions that actually ended up doing the same thing, just retransmit. All right. And so that is the sender side of RDT 2.1, and we'll just not cover the rest of it because it's pretty much the mirror. Okay, the only difference is just that handling data packet 0 versus data packet 1. And this is the receiver of RDT 2.1. You see similarly the number of states and transitions also doubled. Let me borrow the technique I used to describe the sender side. So the line in the middle here actually indicates the upper left and the lower right. They are the mirror of each other. The difference is just that the upper left is handling data sequence number 0, expecting data sequence number 0. And the lower right expecting and handling sequence number 1. And then we propose that we walk through the state machine this way. First, assuming that there are not going to be any data corruptions nor the ACK/NAC corruptions, meaning things are going perfectly. At the beginning, receiver will start from the initial state, wait for packet 0 coming from below. And nothing's going to be wrong there, therefore it will be triggering, this condition, this transition. Okay, so receiving a packet, no corruption, and it's carrying sequence number 0 here. Okay, expecting 0, carrying sequence number 0, perfect. Let's extract the data, pass it up to the application layer, generate the ACK packet, but this time what? Including the checksum. So this is coded in RDT 2.1 because we are now assuming also ACK/NAC could be corrupted. So checksum here is to enable the data sender to be able to check whether the ACK packet or the NAC packet is corrupted. So that ACK packet with the checksum will be generated and sent back. All right, straightforward. And we move to the new state, wait for 0 from below. Similarly, we'll be getting a packet from below, receive RDT, and not corrupted, and carrying the expected sequence number 1. Cool, happy again. Extract data out of the packet, pass it up to the application layer, generating an ACK with checksum, send it back. Upon finishing all these actions, we take the transition, Receiver here, go back to wait for 0 from below. If another packet comes in, not corrupted, carrying sequence number 0, again happy, take the transition, wait for 1 below. And this will go on and on and on and on and on. And when there's no data corruption, when there's no ACNet corruption. Now, what if there's data corruption in RDT 2.0? Yeah, that's where we begin to see these transitions showing in the receiver side of RDT 2.0. This is the case when we are expecting 1, but we get the corrupted data. Then we say, hey, the data is corrupted. Generate a negative acknowledgement, but hey, in RDT 2.1, we do need to include the checksum and send it back to the data center. Similarly here, if we're expecting 0, receiving a packet, it's corrupted. Generate the neg, send it back to the data center. Okay, so these two transitions we know well. Okay, they have already appeared in RDT 2.0. The two transitions remaining, yeah, this one and this one here. So this guy and this guy here. Okay. Just like these two, very similar. These two, very similar. They are actually very similar as well. So let's focus on this guy here. So this is the case when we are waiting for packet 0 to arrive. We did get a packet, it's not corrupted, but wrong sequence number. How can this be happening? Well, then this must be because, hey, sequence 1 here has already been received earlier. That's why we've already moved on to wait for 0. Now, receiver here, receiving 1, will be also sending an ACK back to the data center. But the data center there finds that packet corrupted. Okay? That's when the sender retransmit sequence 1, thinking, I'm not sure, I'll just retransmit. And therefore, we get a duplicate packet here. All right? So if that's a duplicate, no. That's not extract packet, that's not deliver, again, the same thing up to the application layer. So you see here, the only actions we'll be taking is just not extracting data, not passing up to the application layer, but only to generate the acknowledgement and send it back to the sender. Now, is it necessary to generate another ACK? It is, isn't it? Because the previous ACK here, yeah, it was corrupted. So sender there is just gonna think that data might not be there. Data might not be there. To be safe, let's just retransmit. So this ACK here is actually crucial, so that the sender, hopefully the second time, gets the ACK all right and they can move on to what? Wait for call from above for packet 0, because it's now stuck at the packet 1's feedback. So, yeah, this is RDT 2.1. Now let's use a couple of very simple scenarios to demonstrate how the sender and the receiver interact. So this is RDT 2.1, no error case, and the scenario is simply first to send 1 packet, and then second, continue and send yet another packet. So our goal is to find out all the transitions being triggered until it reaches the steady state. Now, in order to find out what transitions each of these finite state machines will be taking, we need to know the starting state. Now, at the beginning of the sender, it's going to start from the initial state. So the starting state will be the initial state for the first transition. Similarly for the receiver, this is the initial state. Therefore, the starting state of the first transition at the receiver side is going to be also the initial state. Now, event is this: send 1 packet. Now, we're here at the starting state to determine what transitions to take let's check out what the transitions are. Well, starting from this state, there's only one possibility, which is T1. And it happens to be what? Getting a call from above, which is to send one packet. So obviously, the first transition we'll be taking is at the sender side, and it's T1. And it matches this event here, and it's gonna complete all the actions listed here, which is to generate data packet 0 and send it out. At this point, sender here enters the wait for AG or NAG 0 state, right? So very important, before you determine what transition to take next, what is the starting state right now? What are the possibilities? Are there multiple transitions one can take from the starting state? If there are, be careful. What is the triggering event? Okay, so pick the transition that's matching the triggering event. And then take the actions, and then finish the transition and land on the ending state. All right, so let me repeat. Starting state, possible transitions, match the triggering event, and then land on the ending state. So now we're done with T1. So the result of T1 is there's a packet being generated, isn't it? And that's going to arrive at the receiver side. Receiver side, currently here. So this is going to be the starting state of the next transition being triggered. And it's receiving a packet from below. So let's see, what are the possible transitions? 1, 2, 3, because all 3 of them starts from the state here. Now, event is, yeah, we receive a packet, definitely. Okay. So all transitions is triggered by receiving a packet. But exactly which one is triggered depends on checking whether the packet is corrupted or not. And we're assuming no errors, so this one is not possible. So this one passed to this point, this one passed to this point. But there's one more check. Is the packet sequence number 0 or sequence number 1? Here, we are generating sequence number 0. Therefore, eventually, this transition waits. And so we'll be taking T11 over here and taking all these actions and moving the receiver to this state. Wait for 1 from below. And now next, right over here, the receiver is generating an AG packet and it's being sent back. So that's gonna trigger an AG packet arriving back at the sender. So sender here currently at the wait for AG or NAG 0 state. See, there are 2 possible transitions. So which of these matches the AG packet with no error? Yeah, this one here. No error, and it's AG packet. So we'll be taking T2 and finish all the action here, which is doing nothing, and enter the wait for call 1 from above state. So sender here goes to this state. And there's nothing to be done here. No more packet being generated flying back to the receiver, so we could have stabilized this right here. So sender here, stop here. Receiver, stop here. Okay? And in the process, we take 3 transitions. First one is T1 at the sender side. Second is what? T11 at the receiver side. And the third being T2 at the sender side.
All right, so that was a very simple example. So quiz 16 here is to try to exercise you for the past like 30-40 minutes of stuff you heard about RDT 2.1 and see here. Let's consider scenario 3. Sender on the left send 1 packet, but there is a bit error in this packet. But luckily, there will be no more bit errors afterwards. No bit errors afterwards, including no more bit errors in data, no more bit errors in AG or NAG. Okay. And this is for the first time more a take-home quiz. So this is going to take you some time. So answers is not expected right now in class today. So we have still 6 minutes to the end of the lecture. But I already borrowed 2 minutes, so we only have 4 minutes left. Now, of course, if you can work with your teammates and come up with the solution today, feel free to go to Slack and type up your answer. Okay, so that was quiz 16. In the meantime, then I can come back to the remaining questions on live chat. One is, so much earlier, Chen Tao asked about why don't we use 2's complement sum? I think the question is very similar to another question that one of the students asked earlier, right? Why 1's complement sum? Why not other type of sum, simply sum? Well, you can use any kind of sum, but the reason that the internet checksum is done in 1's complement sum is more that we could come up with hardware acceleration that's a little bit easier. And then the last question is from Examen Wei. I think this is Sheng Wei. So Sheng Wei was asking, hey, back in chapter 2 when we were talking about the response time, getting a web page, there are many RTTs, and the more RTTs there are, the less preferred by the users. So if we do RTT now, having negative acknowledgement back and having the sender retransmit again, then it adds more RTT to the transmission. And it's right in the middle of the TCP connection, or in the middle of the reliable connection. You know what, Examen, you're perfectly right. Doing reliable data transfer, that's going to add to the delay. And there'll be more RTTs, and you don't know exactly how many RTTs there might be. It really depends on the number of errors or losses we run into. It might not be just one more round trip time. It might be multiple round trip times more. So you are perfectly right. And now you can see why some applications still prefer sending through UDP. So DNS sending through UDP makes perfect sense, because it's something that we must have, the IP address we must have in order for the real data to go out. Okay, good. And okay, Chen Tao is trying to help here. Okay, thank you. So today you see that we actually learn much more in a lecture, in a 2-hour lecture, as opposed to previous weeks. Okay, you can probably appreciate that. No problem. You can probably appreciate that if we mute our questions and delayed it to the breaks, then we can focus on the video, because the videos coming up, entering chapter 3, it gets more technical and it might be a little bit more intensive. It'll be easier for the classmates to focus. So we could hold the question, if we could hold the question to before or after the break, okay, that would be great. Okay, so we can be more focused. And I see that there are some of the teams typing up their solutions. Very good. You see, after thinking about it a while, exercising it a couple more times, this is actually easy. It's just that we are learning a new system, the finite state machine, to describe protocols, to describe mechanisms. All right. Starting next Wednesday, there will be one more quiz, quiz 17, which is very related to quiz 16. That's another exercise, okay? The key to master these finite state machine is just to exercise more, and there's no other trick. Okay, so next week, quiz 17 and 18 will break open the lectures, in fact. Okay, and I look forward to seeing you again next week. And of course, good luck with the exams. Okay, what's nice about doing the lectures online is also that you can always come back to the lectures if you really need the time to prepare for the exams in the afternoon, for example. It's actually okay. You can always come back to the videos. Those who prefer to stay right here with me, because you can ask question and get immediate feedback. You see, this is really nice because then you can clear this and then move on faster. So there's advantages of staying online with me. Of course, there's also advantages that you take a lecture off and then work on something else that requires timely response and then come back to review the video. But then you need to kind of, wait and maybe type up questions on Slack and wait for my answer. All right, good. So you guys are all picking this up. Again, next week, Wednesday, we'll start by Polly illustrating her solution of quiz 16. And then 17 comes up, and then 18 comes up. Very good. So you see, it just takes a little bit of time, but it's actually quite straightforward. In fact, finite state machine is how Turing, the Turing machine Turing, Alan Turing, the father of computer science, used to describe his computer. And that reflects exactly how computer is thinking. Computer actually doesn't create. Computer does think, but it's thinking based on all these finite state machines, the programmers or us implementing to it. So RDT 2.1 here has already been implemented. I've presented to you. You guys now, being a computer, follow the program, follow the machine to handle one particular scenario, yet another particular scenario. You just follow the rules. So these will be, answers should be consistent here because computers don't give two different answers given a deterministic algorithm. All right. So algorithm also can be represented as a finite state machine. And by the way, finite automata, that's a required course in computer science for your information. For the students in EE department, you're probably less aware. So for students taking computer networks, usually the prerequisite includes also the sophomore or maybe junior year required courses in computer science curriculum. All right, then, hey guys, go get lunch. Okay, and enjoy the rest of the day. Ciao. If you have further questions, I see that sometimes I end the session a little bit earlier. If you ask it on YouTube live chat, I would definitely post it back on Slack and provide answers there. Those are going to be on the Ask Us Anything. Okay, so if I go to this channel here, you see, you see here, this was the question from Examen again, but yesterday, and I tried to answer it over here. Finite state, deterministic finite automata. It's a finite state machine. My understanding it's always deterministic, but I can also think of a way to add some probability elements into the condition or the actions. Then it might be a little bit less deterministic. Good question or good comment, Chen Tao. Okay, Zhonghuan was asking something. And then this thing over the top, does it mean that OTT is a kind of service that bypass the network core and connect the host directly to communicate? It is. Yeah, your understanding is correct. It's more just to describe that kind of network, but we are connecting processes at the application level, over the top. Okay, the top layer, the application layer. So you kind of form an application layer network. You can think of it as bypassing, so you don't have to worry about the physical connectivities, okay, of the hosts involving that application layer network. Yeah. And this is often what the users or designers at the application layer see better, because we don't see exactly where the routers are. So if you want to implement an application that kind of connect not just client server, but also secondary server, third level server and stuff like that, having like a network Over the top is how you describe that kind of network. Okay, very good question. I somehow missed this. Very good to know. I'm gonna type up an answer here as well. Okay, bye guys. Alright, so I'm gonna end the stream now. Okay, see you next week.